Alright, hello everyone and welcome to a new problem from the arrays chapter. This one is called smallest difference, and we are given two arrays of integers and we should find the pair of numbers, one number from each array whose absolute difference is closest to 0 and return an array containing them. So in this example we have nums1 and nums2, and the two numbers, the first one is 28, as you can see from nums1, and the second one 26, as you can see from nums2. The two numbers that have the closest difference, the closest absolute difference to 0 is 28 and 26. And why is that? Because their absolute difference is 2, and you can take each and every other pair of integers and you will see that you won't find a smaller one. So let's get straight to the chase. All we have to do for a brute force approach here is just try out each and every number from this array. So just fix the number, and then for that number, try out each and every number from the second array. So fix that number and just compute their absolute difference. And if it is less than our current answer, all we have to do is update our answer array with those two integers. In the end, we will return that array. So let's see how the code looks like. We have our answer array, which is initially empty. This will denote that we haven't tried yet some pair of numbers, right? Then we take each number x from the nums1 array, and for that number x, we try out each number y in the nums2 array, and if the array is empty, so we yet don't have any solution, or this pair of numbers, the absolute difference between x and y is less than the absolute difference between our current solution, then we just update the solution with that pair, and in the end, we return it. What's the time complexity of this approach? Well, this is, of course, constant. Returning an array of two integers is constant. This is constant, checking this is constant, and of course we have these two nested for loops. This one makes a total of n iterations, where n is the size of the nums1 array, and this one does a total of m iterations, so the final time complexity of the brute force approach is big O of n crossed m. Now, of course, this time complexity is big and we want to reduce it, and in order to do so, we have to take a look at what happens in the brute force approach. Well, we basically try out each number in nums1 and each number in nums2. So we will need to get rid of one of those in order to have a faster approach. And I'm just going to get rid of this one. You can also get rid of the first one, but let's say we get rid of this one and we only try out each and every number in nums1 and somehow come up with a faster way of finding the number y from nums2 such that the absolute difference of these two is as small as possible. First of all, one tip that I want to give you guys is that in the 99% of the problems where you have to deal with absolute differences, the absolute difference in itself is not so useful, so we will have to break it down into the two possible scenarios. So let's have the discussion right now. The absolute difference between two numbers, x and y, is equal to either x minus y if y is less than or equal to x, or y minus x if y is greater than x. So instead of trying to minimize this absolute difference, we can try to treat each of the scenarios separately, and for each of them, try to minimize the formula that is correspondent to it. And remember what I've told you, we are still going to try out each and every x from nums1, but we won't do this anymore, so we have to find what are the best y's that we can try out for that specific x. From all the integers in the nums2 array, some of them are going to be less than or equal to x, and some of them are going to be greater than x. Let's solve this scenario first. If we know the value of x, and we want to minimize x minus y, for this expression to be as small as possible, so it has the minimum value, because now x is quote-unquote a constant, we have set its value, what we need to do is find the greatest value of y. So greatest y, such that still the expression has to be valid. So what needs to be happen is that we have to find the greatest y such that y is less than or equal to x. In the second scenario, because x is quote-unquote a constant, in order to minimize this value, so minimize y minus x, what needs to happen is that now we have to minimize the value of y. So find the smallest y, such that still we have to make sure we are, in this scenario, so such that y is greater than x. So what we need to do is try out each and every value of x in this for loop. And for each and every value of x, find what is the greatest y, which is still less than or equal to x, and take this difference, x minus y. And what is the smallest y, such that y is greater than x, and take this difference, and we are going to take the minimum between these two, and that's going to be the minimum absolute difference, which uses x as the number in nums1. Let's take again our previous example. Alright, and for our example, for every value of x from nums1, I've written what is the greatest y less than or equal to x, and what is the smallest y greater than x. For -1, we have no value in the second array, which is less than or equal to -1, but we have all the values which are greater than -1, and the smallest one is indeed 15. So the smallest absolute difference from -1 is 15 minus -1, which is 16. And indeed, if you think about it, why would I take a number which is even greater than 15? The absolute difference is going just to get greater and greater. Now, for 5, again, no number less than or equal to 5 in the second array, but the smallest one greater than 5 is 15. So 15 minus 5, the best absolute difference here for x equals 5 is 10. Then for this 10, again, no number less than or equal to 10, and 15 also the smallest one greater than 10. So here the absolute difference is 5. Then for 20, we have two numbers, 15 and 17, which are less than or equal to 20, and the greatest one is 17. And then we have a couple of numbers greater than 20, and the smallest one is 26. So what is going to be the smallest absolute difference for x equals 20? Well, it is either 20 minus 17, which is 3, or 26 minus 17, which is 9. So we are going to choose 3. Then for x equals 28, we have 26 and 134. So we have either 2 or 106, I think. We are going to choose 2. And indeed, think about the other numbers less than or equal to 28, like 15 and 17. Of course, they will give us a greater absolute difference. And here for 3, no number here, 15 here. So the best absolute difference for this one is 12. And of course, we are going to choose the minimum among all of them, which is 2. We can notice something here. For the first 5 values of x, which are in increasing order, as you can see, the greatest y less than or equal to that x is indeed in increasing order, and also the smallest y greater than x is indeed in increasing order. Then, because the next value is less than the previous one, this won't happen for these two. But if I was to, let's say, introduce the number 3 here, the values would look like this, and the property is still satisfied for these values and also for these values. This is an important hint. If the integers from the first and the second array are in random order, then yes, these values that we are looking for could be in random order. One could be the first one, then the last one, then maybe something in the middle, and so on and so forth. But if we are going to sort these arrays in increasing order, then the positions of the greatest y's and of the smallest y's could be more predictable. Let's sort these two arrays and take a look. Let's iterate through the integers in the first array and see what is the greatest y less than or equal to that integer. Well, for the first value, -1, we don't have any, so we can say that it is somewhere here, just to denote that all the integers here are greater than that value. Then, if we take the next one, it will still be here. If we take the next one, it will still be here. Also for the next one. Then, if we take 20, the next element here is less than or equal to 20. Also the next one. So 17 is the right value. Then, if we take the next one, the next element is less than 28. And this is the value. So after sorting the arrays, we can already notice that the greatest y's for each value in the first array come after another. And this definitely makes sense, right? Now that the arrays are increasingly sorted, of course that if I know that greatest y for one integer, for example, I know that for 20, the greatest y is this one, I always move to the next element, which is greater than or equal to the previous one, for example, 28. So of course, that number is still going to be less than or equal to our current integer, but also maybe there are some other numbers on its right which are also less than or equal to it. So I'm going to look for more, and I find now 26. This already leads us to the idea of using the two pointers technique. If you imagine iterating through these values with, let's say, I, you can imagine that finding this greatest y is indeed finding the max j of that I. What is the greatest index j such that nums2 of j is less than or equal to x? And of course, because this array is increasingly sorted, the greater the j, the greater the y, which is perfect. And as we have seen earlier, max j of I is always less than or equal to max j of I plus 1. So I can definitely use the two pointers technique in order to find the greatest y for each value of x from the first array. Now let's see if I can also do that to find maybe the smallest y which is greater than x. For the first value, minus I, this smallest y is 15. For 3, also 15. Also for 5, also for 10. Now, for 20, I take a look at my element, which is 15, which now is less than 20. Not good. I gotta find a greater one, so I try out the next one. 17, not good. And 26 is indeed the first element which is greater than x. Now, if I move to 28, the current element is less than 28, so I gotta look for the next one, and the next one is the first one which is greater than 28. So what's going to happen now is that for each element, I know this smallest y. For example, for 20, I know that the smallest y greater than 20 is 26. And whenever I move to a new element, that element is going to be greater than or equal to the previous one. So this smallest y could not be valid anymore. Here, because I moved to 28, 26 is not greater than 28. So what I'm gonna do is, of course, look for an element on its right. Here, 134. So noticing that while iterating through the elements of the first array, we always move to the right to find our desired element, this again is a big hint that we should use the two pointers technique. What you should imagine now is that this is the I, the pointer we use to iterate through all the elements in the first array. But now we are not looking for a maximum j, but we are looking for a minimum j. So what is the minimum value of j such that nums2 of j is greater than nums1 of I? So it doesn't matter whether this is a max j or a min j. All that we care about is to make sure that it only moves in one direction. So if I was to make this a pointer, I need to make sure that this pointer will always get incremented or move to the right. Or maybe, in some other problems, this pointer will always get decremented. So I need to make sure that min j of I is always less than or equal to min j of I plus 1. And as we have seen earlier, this happens. There are basically two scenarios that would happen here. The first one is that when we move to the new element, that smallest y that was for the previous element is still greater than our new element. For example, the smallest y for 5 was, what's its value? 15, right? When we move to 10, this smallest y is still a valid one, so it will stay here. Or what could happen when we move one more time to 20, this one is not greater than our element anymore. So of course, I need to move to the right because there I could find an element which is greater. Awesome. And this is how we are going to solve this problem. We will iterate through each element from the first array. And we are going to store two pointers, one pointing to the greatest y in this second array, and the other one pointing to the smallest y also in this second array. And each time we make the transition and go to the next element in nums1, we will move the first pointer to the right for as much as we can. So as long as the next element is still less than or equal to x, then that element would definitely be better because it's greater. So I'm going to move that pointer to the right as long as this happens. Or in the second scenario, I'm going to move the pointer to the right as long as it is needed, in case the value there is less than our current value. Let's take a look at the code. Alright, and this is the code. So the first thing that we do is sort the two arrays, nums1 and nums2. Then we start with our empty array, which is going to store the answer. Then we have our two pointers. P1 is going to be for the greatest y, which is less than or equal to the current element. So, as we have seen in the previous example, because we might have scenarios in which all the elements in nums2 are greater than the current element, I'm just going to initialize this with -1, and the second pointer, P2, which will point to the smallest element in nums2, which is greater than our current element in nums1. I'm going to initialize this with 0, because if the first element in nums2 is greater than our current element, then definitely it will be the answer. If not, I can start from there and just increment P2 until I find one. Then I take each integer in nums1, which is x, and what I do first is update the P1 pointer. So for as long as P1 is less than m-1 and nums2 of P1 plus 1 is less than or equal to x, so basically I try to increment this pointer as much as I can in order to find a greater value which is also less than or equal to x. I increment it, then I exit the while loop, and before trying to update the answer with our new pair, x and nums2 of P1, I have to check if that element actually exists. So if P1 is different than -1, the element exists, and I try to update the answer. Then I update the P2 pointer. So for as long as P2 is less than m and nums2 of P2 is less than or equal to x, so now when I move to a new element, maybe this nums2 of P2 became less than or equal to x. So what I need to do is increment P2 until I either find the first element greater than x, or I don't have any and P2 will become equal to m. This is exactly why, after the while loop finishes execution, I check if that element exists. So if P2 is less than m, then I try to update the answer with x and nums2 of P2. In the end, I will just return the answer. And as you have seen, I've written a function for the updating because it appears twice in our algorithm and we don't want to have duplicate code, right? So update answer of answer x and y. We check if either we don't have a solution yet, or that solution maybe is not as good as this new possible one, x and y. So if answer is empty, or the absolute difference between x and y is less than the absolute difference between these two elements in ans, then I update the ans. And this is it, guys. Now let's see what's the time complexity of our algorithm. First of all, this function takes big O of 1 time complexity, right? We just have comparison, some computations, and one assignment. Cool. Now, let's take a look at the main algorithm. We first sort the arrays. This is interesting because sorting an array of n elements is big O of n log n. And we also sort the second array of m elements. So plus big O of m log m, we will take both of these into account. Then this is constant. This is constant. What happens here? Well, of course, we have only constants, right? The function call is constant, constant here, constant here, constant here. So basically what happens is this for loop, which makes a total of n iterations. We know that for sure. And we have this while loops, which have a variable number of iterations, right? For some x, there could be 2 iterations, 5 of them, maybe none of them. But what we know for sure, based on the 2 pointers technique, is that P1 starts from -1, is always incremented, and is always less than or equal to m-1. And P2 starts from the value 0, is always incremented, and is always less than m. So each of these 2 will be incremented for at most m times, which means that these constant operations from here are going to be performed each for at most m times. So the time complexity of this piece of code, because we also have the for and the whiles, is going to be big O of n, the iterations of the for loop, plus m, the total iterations of the 2 while loops. Awesome. Returning this is constant. We don't care about that. So what basically happens is that we have a big O of n plus m, but before executing this code, we have a big O of n log n plus m log m. As you can guess, n log n is greater than n, m log m is greater than m. So the final time complexity of our algorithm is actually given by the sorting of these arrays, and it's this one. If the arrays, for example, were already sorted in the input, then it would have been big O of n plus m. And that's it, guys. I hope you enjoyed the lesson, and I'll see you on the next one. Bye.